So today I will tell you about the foot experiment, in particular about the design and the performances of the calorimeter of Ticker's experiment. As I said, I'm a PhD student of the Turin University in Italy, and I'm working for the INFN, the Istituto Nazionale di Fisica Nucleare. Okay, so I decided to split my presentation in 3 parts. I will start with an introduction where I will tell you about the topics and about the purpose of my experiment. Then I will speak about the experiment itself, and the last part I will speak about my contribution and the main task of my group inside the collaboration. Okay, fragmentation of target or foot is a nuclear physics experiment, and it wants measure fragmentation cross-section of secondary fragments created in interaction between a primary beam and a fixed target. These measurements will be relevant for 2 main topics, for the hadron therapy and also for the space missions. Okay, just some words about the hadron therapy. The hadron therapy is a kind of radion therapy, so with conventional radiation, but with the hadron therapy, we'll use proton or carbon ions, so hadrons. And this approach has a lot of advantages, and the main one is the profile of the energy released inside the patient. So as you can see in this plot with the blue trend, we can see that the energy released in the entry channel, so on the surface of the skin of the patient, we release low energy, and the maximum of the dose is released where there is the tumor, so inside of the patient. So changing the energy of the primary beam, the treatment particle, we can move this peak called also Bragg peak, and we can scan on all the surface of the tumor. With the radion therapy instead, we have a different profile because we have the maximum of the dose on the surface of the skin. So we can have a lot of advantage with this with the first approach. But there are also some problems with this kind of therapy. The main one is that this particle, for their nature, they can interact also with nuclear force. And so when these particles interact with the atom of the human bodies, they can create secondary particles inside the body of the patient. And so these secondary particles can release their energy in some tissues or organ that maybe you want to preserve. So in order to improve the treatment, these treatments, we need to know very well these processes. So we need to measure the cross-section of these fragmentation processes. Because thanks to these measurements, or better, we can give these measurements to the medical, and the medical can improve the treatment planning system created for each single patient. And so they can also improve the treatment itself. But this measurement will be useful also for another topic, as I said, like in the space missions, because in the space we had similar effect of the hadron therapy, because with when cosmic rays interact with the walls or shielding of spacecraft, they produce secondary fragments inside the vessel, and these secondary fragments will be dangerous both for the astronaut but also for the electronic devices. So my experiment, FOOT, wants to fill the gap in experimental data of these fragmentation processes in different energy ranges. For the proton therapy, so hadron therapy with proton beams, we will do measurements in energy range between 50 and 250 MeV. For hadron therapy with carbon ions, we'll do measurements with beams with the range between 50 and 400 MeV per nucleons. Instead, for the radio protection, we have to extend the energy range up to 400 MeV per nucleons. So the idea is to use proton and carbon ions like beams on a target or carbon or oxygen. But there is a problem with this situation, because for example, if we take protons on carbon or oxygen targets, the fragments will born only from the targets and not from the beam, of course. So in these cases, the fragments will have very low energies, about some EV, and so they will cross very short ranges, about some micrometers, and so they will be not detectable because they will not escape from the target, and so we will be not able to measure the cross sections. So the strategy of the foot experiment is to work in an inverse kinematics. So instead to use a proton beam on a target of carbon or oxygen, we will work in the opposite reference system. We will use carbon or oxygen beam on a proton target. In this case, the fragments will have longer range due to the Lorentz boost. And after the measurement of the cross sections, we can come back in the previous reference system. But there is a second problem, because we can't use a hydrogen target because the density of the gas is too low and also low interaction probability. So we will use a combination of two targets, a polyethylene and a carbon one. From the subtraction of the two cross sections with the two different targets, we can find what we need. Okay, so we can skip to the second part about my experiment. And so I will tell you about the design and the requirements of this experiment. First of all, we are an international collaboration, about 100 people. The biggest part of this collaboration is in Italy, but we have also one group in France, in Strasbourg, and a couple of groups in Germany, at GSI and in Aachen, and one small group in Japan, at Nagoya. Okay, as I say, the goal of our experiment is measure differential cross-section of the fragmentation processes with a resolution below 5%. But in order to achieve this value, we need to identify very well the fragments. So we need to measure the mass of the fragments. And here we have the range of the resolution on the mass. But in order to identify the mass of the fragments, we need to measure three different quantities: the kinetic energy, the momentum, and the time of flight. Combining 2 by 2 these quantities, we can calculate the mass in three different ways. And thanks to this redundancy measurement, foot will be able to exclude the events where the mass is not calculated properly. For example, when we create neutron inside the calorimeter. So for these reasons, we've decided to design the foot experiment like in this sketch. We can start from the left to the right. We have the beam. Then we have the star counter. The star counter, basically, it's a plastic scintillator in order to give the trigger to the experiment, but also the start of the time of flight. Then we have the beam monitor, just basically it's a drift chamber, just to monitor the position of the beam before the interaction point, because after this detector, we have the target. After this, we have the magnetic spectrometer in order to measure the momentum of the particles with three different tracker stations. So three different tracker detectors. We have pixel, and microstrip, and two magnets. After this, we have the so-called, what we like to call top wall, is again a plastic scintillator composed with scintillating bars, vertical and horizontal. And thanks to this detector, we can have the stop of the time of flight, but also the charge of the particles from the energy loss of the particle inside the scintillating bars. The last detector is the calorimeter. Yes. One thing that I want to underline is that the dimension of this experiment is not very big. This experiment is little, as you can see. For example, the distance from the target and the calorimeter is about 1 meter. So the idea indeed of this experiment is to be a tabletop experiment. Indeed, the idea is to move the experiment in different facilities, for example, at GSI in Germany or at CNAO in Pavia. I will speak better about CNAO later. And take data in different facilities with different beams. So now we can speak about the last part of my presentation, the biggest one, about the calorimeter. As I said, it's the main task of my group. So I will tell you about some test beams that were performed during last years in order to make all the design choices for the calorimeter. The main requirements for the calorimeters the main requirements for the calorimeter is of course the linear response of the object of the detector, and the second thing is the kinetic energy resolution. We need a kinetic energy resolution below the 2%. So all the test beam that I will show you will be focused in order to achieve this value. And the last part, I will show you some performances about the detector. All the test beam that we performed were at CNAO, at Fondazione CNAO. CNAO is one of the most important centers in the world where they treat tumor with the hadron therapy. And this facility is in Pavia in Italy. Okay, we can start from the arrangement of the calorimeter. So basically, our calorimeter is a matrix of BGO crystals. Here we have a picture of one BGO crystal. As you can see, it's a truncated pyramid. And we have chosen BGO because it has a very high density. So it means also very high stopping power, and it means that we can stop particle with higher energy also in few centimeters. But the main problem with this object is the weight, because with this density and with this dimension, each crystal is about 1 kilogram. So it means that the full object is about 300 kilograms, more than 300 kilograms, because we will have 320 crystals. And the second problem is that we have to move it in different facilities. So the idea was to split all the detector in different substructures called module, where each module is composed by 9 crystals, so only 9 kilograms. Okay, the calorimeter is a scintillating calorimeter. So it means that in order to know the energy of the initial particle, we have to collect all the photons created from this particle inside the BGO crystal by ionization processes. So we can think, for example, to have a fragment or a particle beam that enters in the BGO, and it loses its energy, so it creates photons, and we can collect photons with a photodetector. So then we can process it with the ReadOut board, the digitizer, and we can take the pulse of the initial fragment. So from each pulse, we can know two main informations: the amplitude and the charge. The amplitude, like the difference between the maximum amplitude and the pedestal, and the charge, like the integral of the pulse. And of course, these quantities are proportional to the initial energy. So what we've done in each test beam in order to make all the design choices was to, as I said, calculate the kinetic energy resolution and the response of the linear response of the calorimeter. So what we've done was shot, for example, beams with unknown energy inside BGO crystals, and calculate the amplitude or charge distributions for the specific energy, as you can see here, for all the events that we've acquired. So from each amplitude distribution or charge, we have performed fit with a crystal ball function, and we have extrapolated the average value, so the mean value of the Gaussian peak, representing the initial energy of the beam, and also the energy resolution from the ratio between the width and the kinetic and the average value of the peak. So the first test beam that I want to show you is the first test beam that we performed some years ago in order to choose the best photodetector for our purpose. So we have decided to work with the CPM. So just some words about CPM. A CPM is a silicon photomultiplier, so it means a single photon avalanche diode, like a SPAD. And it means that a CPM is a matrix of these SPADs, where each SPAD works in a mode called Geiger, in a Geiger mode. So it means that the gain of each SPAD is very high because the bias voltage applied to each microcell is really high. So it means that each microcell can count only one photon in a specific time, in a specific interval. So this detector is really useful if you want to count photons, because the number of photons will be the number of the cells activated, the microcells activated. But there is a problem with this object, because if you have more photons than the number of microcells, you will get a saturation. So we have performed this test beam in order to understand which was the best silicon photomultipliers for our purpose. So we've tested different silicon photomultiplier with different size of microcells in order to understand which was the best one in order to cover the full energy range foreseen by the foot experiment. So what we have done was shot carbon and proton beams with these energies, 4 energies with proton and 5 energies with carbon. And then we have measured the energy resolution and also the linearity response of the crystals for this energy. So here we have some results about this test beam. In this plot, we have the linear response only with the 5 energy of carbon beams for the 3 different silicon photomultipliers. I didn't tell you, but we are not using a single silicon photomultiplier like this, but we are using a matrix of this one. So what we call tile. So in red, we have the silicon photomultipliers arrays with 15 micrometers, in blue with 20 micrometers, so like the size of the microcells, and in green with 30. As you can see with the last one, with the green one, we have optical saturation. So we've decided to work with the first one with the 15 micrometer, because we can have also an extra safe factor if we want to extend the energy range of the beam up to 800 MeV per nucleons for the radio protections, for the radio protection measurements. In this case, the points represent the average value of the Gaussian peak that I showed you before here. So the linear response in terms of amplitude in this case. On the right side, instead, we have the plot related to the energy resolution. So as I say, the ratio between the width and the average value of this Gaussian peak. As you can see, here we have the points related to the carbon beams, and here the points related to the proton beams. As you can see, we've got good results because except for the lowest energy, we have achieved the energy resolution below 2% for all energies. And the different color represent the 2 different analyses that we've used. So in black, the charge analysis, so the integral of the signals; in red, instead, the amplitude. And here we have a picture of the final configuration of the CPM and the readout boards. So in the experiment for the detector, we will use a matrix of silicon photomultipliers 5 by 5 with a pitch, as I said, of 15 micrometers with these dimensions. So we've decided to work with silicon photomultipliers because they are really small, as you can see from the picture. And so they can help us to have a really compact design. And the second thing was they work with really low voltages compared to other photodetectors like standard PMTs. Okay, the second test beam that we have performed was in order to choose the wrappings of the crystal, because thanks to the wrapping, we can collect as more photons we can. So in this test beam, again at CNAO, Fondazione CNAO, we use for the first time a module of the calorimeter, so 9 crystals together. And we have equipped the different rows of this module with different kind of wrappings. In the first one, we used a reflective painting. In the second one, we used Tyvek papers. And in the last one, a wrapping called mylar, a kind of aluminum. So again, what we have done was shot the beam with the same energy used for the previous test beam. So the 4 energies for proton and 5 energies for carbon in the different crystals. And we have again measured the kinetic energy resolution for each different energies and also the response of the crystal. Here we have some pictures about this test beam. Here we were in the treatment room of the CNAO. Here there is a treatment bed, and here there is the module with the beam line, with the laser of the beam line. Okay, in this slide we have some results about this test beam. On the left, we have the plot related to the linear response. So the average value for the of the Gaussian peak for calculated with the amplitude analysis. Each color represents a different wrappings. In green mylar, in blue Tyvek, and in red reflective painting. And as you can see, with the Tyvek, we can reflect more light inside the crystals, and also it means collects more light. And collecting more light, we can also obtain better energy resolutions. Okay, not much in the carbon because are pretty the same for all wrappings, but we have better resolution in particular for the proton energies, so for the lower energies. So we have decided a second point for the design of our detectors, the wrappings after the photodetector. Okay, in this slide, I wanted to show you some picture about the mechanic. Here we have an older related to one single module. Basically, is a box with 9 holes, so 1 for each crystal. Instead, here we have the idea of the full calorimeters. As you can see, we have all the modules and the structure to all the modules, and also the HV and low V board related to the voltages. So thanks to all these parts, these pieces, we have made all the design choices for our calorimeter, the silicon photomultiplier, the ReadOut board with the same dimension of the silicon photomultiplier, so the design is really compact. The wrappings, the ADC, the digitizer. I didn't say anything about this, but we have performed a lot of tests about the digitizer in order to understand if we wanted to do pulse shape analysis or not. And finally, the mechanics. With all this information, we have achieved our goal. So in the full energy range foreseen by the FLUKA experiment, energy resolution below the 2%. And here again, we have the double markers, one calculated with the amplitude analysis and the second one with the charge analysis. Okay. About the linear response, we have some issues because here we have the average value related to the amplitude distributions for the carbon beams, and here for the proton beams. So dividing these points by the mass number of the carbon in order to compare better the two trends, we can see there is a problem because the response of the calorimeter depends on the A and zeta of the incident ions due to the Birk's law. So it's a problem because from a certain amplitude or charge, we can't know the initial energy of the fragments, because for a specific value, we have two values in energy. So it's a big problem, but we think that for this, we can't do anything, but we can solve this problem thanks to the other detectors in foot. For example, from the detector in front of us, the top wall, the plastic scintillator, because the top wall can give us the zeta of the particle from the energy loss in the scintillator bars. So from the zeta of the particle, in principle, we could distinguish between different ions, but more tests will do it for this study. And the second thing is the calorimeter response for each different ion is not perfectly linear, in particular if you look at the carbon points. So in order to understand better this thing, we have performed another test beam at CNAO. And this time we have placed two PGO crystals rotated by 90 degrees compared to the beam line of CNAO. So we performed a scan with the beam along the length of the crystal, 3 centimeter by 3 centimeter. So we've started in 15 millimeter, so in the fastest point from the silicon photomultiplier, up to 215 millimeter, so very close to the silicon photomultiplier. Why this? Because we wanted to understand if the response of the crystals depending or not with the depth of the particle inside the BGO crystal. So we used two beams, again, proton and carbon, but only for energies. 70 MeV for proton and 150 MeV per nucleon with carbon, in order to have the Bragg peak inside the first crystal. So in order to contain the full range of the particle inside the first crystal. With 170 MeV and 260 MeV per nucleons instead, in order to have the particle inside the second crystals. For this case, so we have summed up the light, in the two crystals. Okay, here we have the results about this test beam. So we can see that with different colors, we have the different particle and energies. For example, in red, we have the scan with the carbon 115 MeV per nucleons. And we can see that the light collected is not constant, but more we are closer to the CPM, less light we have collected. So the results was a little bit unexpected, because we thought a constant response, or at least the opposite trend. When we are closer to the CPM, we could collect more light. So first of all, we've tried to understand if this effect doesn't depend from particle and energies. So in this plot on the right side, you have the ratio between the amplitude or the charge, of course, acquired in the different position, normalized to the amplitude in the first position. So I just normalized all the points to the first one. And as you can see, this effect is the same for all particles and energies. So at least this effect doesn't depend from the nature of particles. One hypothesis about this that we thought was that, for example, if we imagine to have the beam here, so very far to the CPM, we can imagine that the light is divided into components. One directly to the CPM, and the other one go to the opposite side. But the problem is when we are here, when the first component directly to the CPM is really short, but the other has to do almost the double of the length of the crystals, and so it has to do much more reflections respect the first point. In order to investigate better this effect, I performed some Monte Carlo simulation, in particular with FLUKA, with FLUKA software. So what I did was simulate, create the geometry that we used at now, this time only with a single crystal and not with two crystals, but again rotated by 90 degrees compared to the beamline. And I simulated the beam position the same that I used at now. The core of the simulation was the tuning of three different parameters. First of all, the wrappings of the crystals, so the reflective index of the Tyvek, and then also the absorption coefficient and diffusion coefficient of the BGO crystal. So after fine-tune of this tuning of these parameters, I found the best one that can allow me to get a good agreement between data and Monte Carlo. As you can see from this plot, in black we have the data acquired at now with the circle for the 70 MeV, with the triangles for the 150 MeV per nucleus carbon. And in red, we have the Monte Carlo simulations. So we can see that the agreement is within the 5%. Yes, I simulated also the silicon photomultipliers, but only as a active area inside the BGO in order to count the number of photons collected in this area for the different beam positions. From the simulation, I also calculated the number of reflections inside the BGO crystals. For example, in this slide, we have an example of path for 5 scintillation photons in the two extreme positions. So in the fastest position from the CPM in 15 millimeter, and in the closest position, so in 225 millimeter. As you can see, the reflections here are much more compared to the first position and also the other positions. And this is confirmed also in this plot, where we have the number or average number of reflections versus the beam positions. So our hypothesis was true. So if we have more reflections, also the probability to be absorbed inside the BGO is much more higher, Okay. So what I did after this was to understand, because this problem is also related to the geometry of the crystal. So I tried to understand if there was a geometry of the crystal in order to compensate this effect. So I simulated again this effect with different geometry of the BGO crystals. So here we have the standard one, the BGO that we have in foot. And I changed the rear face of the crystals up to an extreme case with a parallelepiped. So I found that with a truncated pyramid with a rear face of 23 by 23 millimeter square, we can have a constant light collected. So with this geometry, we can compensate within a 5% the absorption inside the BGO. But anyway, we have this problem inside the BGO crystals. We have this BGO, we don't have time to modify the geometry, cut the crystals, etc. So we need to compensate this effect offline with some correction method. So I performed other FLUKA simulations, and I performed in this time simulation in order to know the range of the particle inside the BGO crystal. So here you can see the position of the range, so the Bragg peak of the particle inside the BGO for the five standard energy used up now. And here the position of the Bragg peak for the energy of proton used again at now. With the triangles, instead, we don't have the position of the Bragg peak, but let's say the center of mass, if you want, like an average distance of the emission of the photons, because we know that, of course, the most part of the photons are emitted in Bragg peak, but we can assume that some photons are emitted also before. So we have also the position of the center of mass. Okay, from these plots, we can calculate the correction for our linear response. So, for example, we can take one particle like carbon with 400 MeV per nucleon, and we can know directly that its range of the center of mass is 4 centimeter. So, from this 4 centimeter or 40 millimeters, we can know directly the amplitude, so the light that we collect with the average amplitude, so the average photons that we can collect with this energy. Of course, we can use one of these trends because we have seen that the effect doesn't depend from particle and energies. And also we can take the amplitude if this effect would be not present. So if the particle crosses 0 millimeter inside the Bigelow crystal. From the ratio between these two values, we can find the K factor in order to correct the amplitude. So in here we have the linear response of the calorimeter after the correction. So after this formula. In black we have before, and in green we have after the correction. As you can see, both from the chi-square of the linear fit on these points, but also from the ratio between data and the evaluation of the fit, we have improved a lot the linearity response. Okay, in conclusion, all the results of the test beam up now were crucial in making all the calorimeter design choices. As I said about the crystal size, the wrapping, the photodetector type and configuration, the ReadOut parameters. I didn't speak about temperature variation compensation, but I have also some information, the backup slide, if there is time, about this study. The DAQ that I didn't show you anything, I'm sorry, and also for the mechanics. With all this information, we have achieved our goal in terms of energy resolution, and we have obtained also a good linear response in the calorimeter, of course, after the particle position. There is still the problem about the Birk's law about the response for different ions. But for this, in the future, there is planned a test beam at the Heidelberg Ion Beam Therapy Center in order to measure the crystal response function with different ions, with hydrogen, helium, carbon, and oxygen. So in a facility where we can have a lot of sources. Then also in the future, in the next month, we will calibrate, we will proceed with the calibration of all the 320 Bigelow crystals at CNAO. So we will calculate the intercalibration factors for each crystal. And in July, there will be a very important test, GSI in Germany, with all the subdetectors. So thanks to all this information, the construction phase of the wall calorimeter can be started.